In this video, I'm going to go through one of the problems from your textbook, but I'm going to approach it a little bit differently than it did. For this handout, that very first paragraph is just giving you a mindset of what's going to be accomplished in 12.2. At this stage of the game, you already have an idea of the flavor of the section. So I'm going to start off by reading the problem. Imagine that you have been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You're also aware that using delicate scales to try to weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while on the boat. What you need is a way to convert the length of the fish to its weight. So this is the raw data that we're giving. You contact the nearby marine research laboratory and they provide reference data on the length in centimeters and weight in grams for Atlantic Ocean rockfish of several sizes. Alright, next thing we have here is on the left is a scatter plot that shows the raw data, and it has a line of best fit drawn in. The graph to the right is the residual plot for that particular data in that particular line. So clearly, from looking at the scatter plot, it fails the common sense check. This data is obviously not linear. That's confirmed by a residual plot that has a definite curved pattern to it. One thing to take note of here, that R squared value of 0.895 is pretty close to 1. So in many circumstances, we'd be very happy with that R squared value being that good, or that close to 1 rather. But that number by itself doesn't mean anything if other conditions don't get met. And this is a good example to emphasize that. Just because you have an R or an R squared that's close to 1 doesn't necessarily mean that we have a good fit here. Alright, so what we're going to do is look at what are some different transformations that could occur. Your book did similar ones to these. These are the ones that typically, if you're going to see this on an AP test, would be the transformations they'd be asking you to consider. So with an exponential model, what you're going to look at is x and ln of y. For a logarithmic model, it's ln of x, y, and then for a power model, it would be ln of both. I believe your book looked at this and they used base 10. You can use log base anything you want. That's a user choice, unless you're specifically told what to use. But if you're the one deciding what type of transformation to consider, you can take log base whatever. Typically, you're going to choose 10 or E because those are the buttons you have on your calculator. All right, next page. First paragraph's up here. We have the exponential transformation, which means you're going to look at x and the ln of y. Graph on the left shows the scatter plot with the line of best fit for that transformed data, and that fails the common sense check. Clearly that data is still curved. Clearly that line doesn't fit it very well, and that is emphasized by the fact of we have a residual plot that has a definite curved pattern to it. Once again, we have an R squared value pretty close to 1. Clearly, this is not a good fit. That R squared value by itself means nothing if other conditions don't get met. Specifically, it fails the common sense check. Specifically, it fails the test of we do not have a random scatter in our residual plot. Okay, second transformation, the logarithmic transformation. This actually made it worse. It exaggerated the curve in the wrong direction. It gives the scatter plot of the transformed data with the line of best fit for that, with the residual plot, and clearly it's failing the common sense check, it's failing the residual plot check. This is not a good model for this data. Okay, third possibility we're considering. A power transformation. That's where you have the natural log of x and the natural log of y. If you look at the scatter plot on the left, the data appears to be pretty linear. That line of best fit appears to fit it pretty well. And looking at the residual plot, we definitely appear to have a random scatter. So that all around looks pretty good. Now, using the R-squared value, that's valid here because it does pass the common sense check, as I like to call it. We do have random scatter in our residual plot. That R-squared is equal to 0.999 is a valid thing to use. Now, of the three R-squared values we had the 0.999, the 0.706, the 0.928. So if that's the only thing we had to go on and not have the residual plots to look at, of those three options, the one that's closest to the 1 is the one that we're going to choose, the logarithmic. The one that's the furthest from the 1 we're choosing the power. The one that's furthest from the 1 is the logarithmic. That had the R-squared value that was the furthest from 1. All right, bottom of this handout. Suppose a contestant in a fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. Use the model that you believe is most appropriate to predict the fish's weight. So the one that's most appropriate, and it's not really even up for a debate, is the power transformation. So that's the ln of the weight is equal to 3.049 times the ln of the length minus the 4.374. The particular software that I use to produce this graph uses the traditional MX plus B format as opposed to the A plus BX that we use in STAT. It's not a big deal. You can just flip it to match the format of the book. Alright, so our task at hand here is we want to predict the weight of a fish that's 36 centimeters long. So putting that line of best fit for the transformed data into AP format, the A plus BX, our equation looks like that. We need to plug the 36 in for the length. That gets us to here. Now that entire right-hand side right here, that can just be typed in as is in your calculator. That's just type it as it appears. So that, showing all of the decimal places that appear on your screen, gets you to that number that's about 6.55. So it's the natural log of the weight equals that number. So to solve what's remaining, we're going to rewrite that exponentially. That's e to that 6.55 power is equal to the weight. We would prefer to solve these without any intermediate rounding errors. So probably the best thing to do is after you get this, then hit E to the answer on your calculator or store that value in an alpha, and then that would avoid any intermediate rounding errors. So showing all the decimal places as they would appear on the calculator, that means our weight is about 700.7 something something something. So we'll round it to one decimal place. The predicted weight is about 700.7 grams. When you answer this as an AP free response question, make sure you say predicted weight. If you just say weight, that implies an observed value rather than a predicted value. Always have the about or the approximately, and the units are considered a pretty big deal. You want to make sure you have the appropriate unit. In this case, the weight is in grams.